Differentiation formulas. So these are the workhorse formulas that you actually use in differentiation. Pretty much, you never see limit again for the next 3 years. You don't. Limit is the foundation that you need to get differentiation. But once you know differentiation, you're never going to go back and use limit for most of the cases. So this is in chapter 2.3 and 2.5 in our textbooks. We actually won't be covering all the formulas today. We are covering the formulas in these 2 chapters. There are a few more that we're going to cover next week. So start with the simplest one. If you have a number, and you're trying to find the slope of that number, what would the slope be? So what we think is you have a function that's just always equals to a number, right? If you have a function that always equals to a number, that's what it is. It always equals a number. What would the slope be? It's flat, right? y2 minus y1 is always going to be 0. So slope equals 0. So this rule is very reasonable. The slope of a number is 0, which you can see from a diagram. You can also use the definition of limit. You can use the definition of the derivative. Find that. So d dxc equals to limit as h approaches 0 of. So here's the part where d dxc equals to limit c minus c over h, right? Which is just equals to limit as h approaches 0 of 0, which is just 0. Okay, so this is a proof. This is a proof. It's a very simple proof. We're going to go through the proofs of the simpler rules. So the more complicated rules, we'll use intuition. So the slope of a number is 0. There is no slope. Next would be more cases where you actually have a variable. Power rule. The power rule says that the derivative of x to the power n equals to n times x to the power n minus 1. Now notice that there is no limitation to this rule in what n has to be. It doesn't say n has to be positive integers. Right? So this rule is more general than just terms of polynomials. Right? It's much general than that. It could be negative numbers, it could be decimal numbers. However, at this point, in terms of what we can do to show why it's true, we can only show why it's true for polynomials. Let's first use the case that let's think about the simplest case, right? Now, the simplest case would be polynomial of with the power being 1, right? But if the power is 1, then it's quite easy to see that what you have is a upward sloping straight line. And it's quite easy. We all know the slope equals to 1 in this case. So yes, this case is easy. But beyond this case, it's a bit hard to figure out what the slope is from a diagram alone. So we're going to, for the case of positive integers, we can actually quite easily show why this is true. So for positive integers, this is one example where it's easier to use the original 2-point formula to see why it's true. Right, so d dx fx equals to limit as you will see, I'm using the original formula. Fx minus fa over x minus a. Substitute in the formula, you have xn minus an over x minus a. Now what do we do? Well, there's one thing you can do because, sorry, the limit. There's one thing you can do because you can actually factorize xn minus an into two parts. And I need a bit more space, so I'm going to push it a bit out further out. You can pull out x minus a, and then what you have left is xn minus 1 plus xn minus 2 a plus dot 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 x an minus 2 plus an minus 1. You can actually do that over x minus a. So you cancel out the x minus a. You're left with limit x approach a of xn minus 1 plus xn minus 2. Well, actually, because of space reason, so let me just not write this down again. You can see that from above. I'm just going to directly substitute. Once you cancel out the x minus a, what you're left with is a polynomial, right? So you can use the direct substitution rule. It's a polynomial. xn minus 1, xn minus 2 times a constant, plus blah, 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 blah. So this is a polynomial. So you can use the direct substitution rule. So you use the direct substitution rule, and what do you get? You get an minus 1 plus an minus 2 times a plus dot 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 plus a times an minus 2 plus an minus 2. An minus 1. So what you have here are actually a bunch of an minus 1, right? They are all an minus 1. The first term, an minus 1. Second term, an minus 2 times a. That becomes an minus 1. Third term, an minus 3 times a squared. Is also a squared. So it's also an minus 1. What you have here is, if you count the number of terms, you're going to have, you have an minus 1 here. That's what you have. You have an minus 1 here. So you group them together. So technically, I made a tiny mistake. This should be a, to be accurate. This should be a. Right. So, and this is also a. So, yeah. Oh no, that's all right. No. Well, okay. This is actually not even very accurate. So I should say, what would be accurate be? This would be accurate. ddx fa is not very clear what it means. So this is accurate. F prime a. This is accurate. F prime a equals to. So that means the derivative of fx at point A equals to the limit of as x approach a blah blah blah, and then you get an to the power n minus 1. So in this example, I use the original 2-point formula and the limit and find the limit of that, and you can actually see that it's going to be a times n to the power n minus 1. I've only shown it for positive integers. Obviously, the same method won't work for negative numbers or decimal numbers, right? Because you can't expand. You can't factorize like that with its decimal. We can show that next week after we have learned more rules. So that's the power rule. Next, constant multiple rule. That says that if you multiply a function, if you scale up a function by a constant amount, then you can scale up the derivative accordingly. It makes a lot of sense if you think about it. Let's say this is fx equals x, and you scale it up. This is 2fx. It's quite, I think graphically, it's quite reasonable to say that if you have a slope equals to 1, then you have a slope equals to 2, right? But this, while for straight lines, it's easy to see this is true. It's not as easy to see that this is true for curves, right? Right. So this rule holds for any differentiable function. So if you have a curve and that has slope s, and you scale it up, well, this couldn't be a constant, so I shouldn't use a single number. So what it says is the slope is g prime x. You scale it up by c, then the slope would be cg prime x. That's what it says. And you can, once again, you can show it very easily with the definition of limit. So d dx cfx, what would it be? It would be the limit as h approaches 0 of cf a plus h, x plus h, sorry, x plus h minus cf x over h. Well, you have a c here, you have a c here. There's no reason why you can't pull them, you can't group them, right? So you can pull out the c. What we are doing is really we are applying the limit laws that we have learned last week. But then, as I said last week, you don't need to state what limit law you are using as long as you are doing it correctly. So, as we have learned from the limit, the textbook does list out all the limit rules that it uses. So you can refer to the textbook, but in an exam, you don't need to. So there's nothing very special. There's nothing special here. You have a constant multiplied by a function according to the definition of the derivative and limit laws. You can pull out the c outside, and then that's what you get. One more rule. Sum rule. If you have two functions, say x equals to 1, or maybe I should give them a name. Fx equals x, fx equals 2x, sorry, gx. And then you have fx plus gx. Well, if you do that, it's quite clear that the slope would be 1, 2, and 3, right? So you can sum up the slopes if you sum up the functions. And that holds for any curves that you can think of, right? So you could have a very weird shape function. And you sum them up, then they would be, so it's kind of hard to draw it accurately. It would be something like, right. So you can sum up the slope. You can sum up the slopes if you are summing up the functions. Okay, can you show that's true? Once again, it's very easy to show that's true. So let's say jx equals to fx plus gx, right? Then you take the derivative of jx. By definition of the derivative, there's the limit as x approaches 0 of x plus h minus jx over h. And then you just substitute in what j really is. So substitute in what j really is, and then you get f x plus h plus g x plus h minus f x minus g x over h. By limit laws, you can group the terms. So you have limit h approach 0 of fx plus h minus fx over h plus limit h approach 0 of gx plus h minus gx over h, and that's equals to the derivative of each individual function. Okay, so all these rules are actually quite easy to prove that they are true. And as I said, once you understand that how they come about, you don't need to deal with this anymore. You just memorize the rules. Once you memorize the rules, they become very convenient to find slopes for any functions that you would come across. Okay, so up to now, what can we do? So what is the slope of, let's say, you have a quadratic function. You want to find the slope of it. What can you do? d dx x squared plus 3x minus 2. Technically, what you need to do now is to use the sum rule. Use the sum rule to make this one derivative into 3. But in practice and in assignments and exams, you don't need to explain what you're doing as long as you do it correctly. So here you just directly, now you could technically do this. As I said, you could technically you can technically do this. This would be correct, but it's unnecessary. It's unnecessary. In practice, what you directly do is just do these individual steps immediately. So what do? In the first step, in the first term, you need to use the power rule and equals to 2x. Second term, you also use in the second term you use the constant multiple rule, and you have 3 ddx. You have 3 times d dx x. Then you apply the power rule again. And then the last one is the constant function, is the derivative of a constant function, so that's just 0, right? So that's just, ooh, why is it suddenly green? So it's just 2x plus 3. So even though theoretically what you're doing is you're applying the sum rule, then the power rule, then the constant multiple rule, then the power rule again, and then the derivative of constant function. You don't need to write out every single step. It's completely okay in this course and in all other courses to go from this step here, a quadratic equation, a polynomial in general, directly to the answer. You can do that. Don't need to explain. It's simple enough. It's like multiplication table. You don't need to justify that you are using the multiplication table. Everyone understand that the multiplication table is correct. What if you have square root of x? And minus 1 over x? What do you do? Well, we don't specifically have rules for them, but do you know that square root of x equals to x to the power 0.5, and 1 over x is x to the power -1, right? So you can use the power rule. So the power rule works for all of them. So for the first term, you have x to the power 0.5. So the power rule says that would equal to 0.5 times x to the power 0.5 minus 1. So that's negative 0.5. And then the second term, x -1, the power rule says you get -1 x to the power -1 minus 1. That's -2. Okay, all right. So this is where it comes from. And once again, what are you doing? We're using power rule, but you don't need to state that you're using power rule. So if you want, at this point, you can indicate that you're having 0. You don't need to do this in exam, but it's up to you. If you want to put it in a nicer format. So that's 1 over 2 times root 2. Oh, sorry, 1 over root 2 times root x, and then plus 1 over 2. Okay, 1 over x squared. The rules of differentiation. The rules of differentiation gives you very easy way to find the slope of any functions you come across. So these are the first 4 rules, and then now we're going to move on to some of the more complicated rules. The product rule. The product rule says that if you have 2 functions and they are both differentiable, then their product is also differentiable and the derivative equals to fx multiplied by the derivative of gx plus gx multiplied by the derivative of fx. Or, in a more compact notation, the derivative of fx multiplied by gx is fx times g prime x plus gx times f prime x, right? So this is something you memorize, but why does it make sense? It's quite easy to memorize. Because in this particular formula, the order where you add things does not matter, right? You just remember, okay, you have to take the derivative of each function and multiply them with the other function, and before summing them up. So it's easy to. This one is actually quite easy to memorize. Fx g prime x plus gx f prime x. It's quite easy to memorize. But why does it make sense? Why does it make sense? Let's see what it's saying. What it's saying is this: the rate of change of fx times gx equals to fx multiplied by the rate of change of gx and plus gx multiplied by the rate of change of fx. If you look at it this way, you have 2 functions multiplied together. what would be a best graphic? What would be the best way to represent them graphically? An area. You have fx as the height, gx as the width. Fx times gx would be the area, and this area is changing. You're interested in finding out the rate of change of this area. The increase in height is f prime x. The increase in width is g prime x. The change, which is this pink area, right? The change in the area is this pink area. You can separate it into three parts. First part, the width times the change in height. That's gx times f prime x. This term here, the first term. The second part of the change in area is the height times the change in width. That's fx g prime x, which is the second term in the product rule. There's a third area in this diagram, f prime x times g prime x, which is the change in height times the change in width. And it's missing from our product rule, right? Our product rule only has two terms. The first term is this purple area. The second term is this blue area. So it's representing part of the change, but it's not representing the whole change. Why would that be the case? Why would that be the case? Why is there not a third term? Why is there not a third term? Remember what we're doing here. What we're having here is an approximation, right? We are approximating the rate of change, and the approximation is accurate. It's completely accurate when the change it's very, very small, infinitesimally small. This diagram that I drew is not small, right? To make the effect salient, I have shown you a really big change. So this is not what the product rule is trying to get accurate. The product rule is accurate for very, very small change. It's not accurate for big change like this one. So let's see what happens with a smaller change. Okay, this is a smaller change. And these are the corresponding areas that we have last time previously. Have you noticed that how fast the areas are getting smaller? In particular, notice how much smaller the black area is versus the other two. If you look at it, I would say the purple area is roughly one third of the previous big change, right? This purple area here, the smaller one, this smaller one. This one. I would say it's about one sixth of the original larger change, right? And similarly, the blue area here that represents fx g prime x is probably 1/6 of the original area, right? Or the larger change. But what about the black area? This black area, I would say, is much smaller. It has gone much smaller. It's about 1 out of 36, right? The ratio of this tiny black area versus the bigger black area is about 1/36. So what you see here is that this black corner that represents the product of the rate of changes is actually shrinking very fast, much faster than the other two parts. So it's shrinking fast. is shrinking very fast in a magnitude higher than the other two parts. These two parts you can see, they are shrinking proportionate to the change in the area, right? They're shrinking in proportional to the change in the length and the height. If the height goes down by a third, these areas go down by a third. If the height goes down by a sixth, this goes down by a sixth. Actually, they go, well, actually, not say, no, they're faster than that, right? They're going down proportional to the rate of change of the height and width. So as the height goes, as the change in height gets smaller, this area becomes smaller proportionately. As the width becomes smaller, the blue area becomes smaller proportionately. But the black area here goes down twice as fast. Well, actually not twice as fast, much faster than twice as fast. If this area goes down at the rate that is the product of the rate of change of the change in height and the change in width. So it's going down a lot faster, you can see. It's shrinking very fast, much faster than the other two parts. As you shrink down, and as you look at smaller and smaller change in area, the black area would approach zero a lot faster than the purple area and the blue area. So it's okay for the product rule to ignore it because this area is going to approach zero very fast. This area is much smaller than the other two areas. So it's okay to ignore it. And it's completely accurate when you're talking about infinitely small changes. So shrinking slow, shrinking slow. Right? So that's why the product rule makes sense. And the product rule is very useful. When you have polynomials like that, you don't want to expand them. This is something that you want to do. This is actually, this is something very important. When you have polynomials like that, and you're asked to find the slope, do not expand them. Do not expand them, because you are very likely to make mistakes if you try to expand them. Instead, use the product rule. You can use the product rule, and it says that what you have here is the order you differentiate does not matter. As long as you differentiate both functions in turns, then it's okay. So I'm going to use the second polynomial multiplied by the derivative of the first polynomial plus the first polynomial multiplied by the derivative of the second polynomial. Right? So there's nothing to do with the first term. Take the derivative of the second term, and once again, technically what you're going to do is you're going to apply the sum product. You're going to apply the sum rule to break apart the brackets, and then you're going to use the power rules and the constant multiple rules and so on. But in practice, you just directly write down the derivative. X cubed. According to the power rule, what you get is 3x squared. 4x, according to the constant multiple rule, you get 4 times d dx x. And according to the power rule, d dx x is 1. So you get 4. And then minus 5 is just going to be 0. Right, so it's going to be 0. You don't need to do that in exams. Once you just write down what it is. Okay, so similarly, x to the power 6, according to power rule, is 6x to the power 5 plus 2x becomes 2, negative 4 becomes 0. So in this course, you don't need to expand. You just write down the final answer like this. There's no point in expanding. It's very easy to make mistakes. So we're just testing you whether you know how to do differentiation. So that's okay. No need to expand. If you're actually interested in finding what the value of a slope is, you can plug this formula into a graphic calculator or computer anyway. So there's no point in expanding this polynomial. Just time consuming. Okay, so product rule is easy to remember. You have the next one, quotient rule, the quotient rule. The quotient rule is hard to remember, for me at least. Quotient rule is hard to remember. So quotient rule deals with division. If you have two functions, gx and fx and gx, and they are both differentiable, then if you want, you can find the slope. You can find the slope of fx divided by gx by this following function. You can find it with this following: gx multiplied by the derivative of fx minus fx multiplied by the derivative of gx divided by gx squared. Or equivalently, you can write gx f prime x minus fx g prime x divided by gx squared. It's hard to remember because this time around you can't get the order wrong. Gx must come first. The denominator must come first. And you have to do the derivative of the numerator first. You have to, so the order cannot be wrong. It's just something you memorize. It's very useful because when you encounter cases, things like this, x cubed minus 4 divided by 2x plus 1. These are cases that you cannot simplify. So it's very hard to figure out the slope of this with any other method but differentiation. So the derivative of x cubed minus 4 divided by 2x plus 1, according to the quotient rule, what you do is put the denominator first, then differentiate the numerator minus the numerator, multiply with the derivative of the denominator divided by the denominator squared. That's 2x plus 1, 3x squared minus 3x squared, no minus, because the negative 4 becomes 0. Minus x cubed minus 4, derivative of 2x plus 1 is just 2. In an exam, in our exam at least, we will accept this as an answer. This is okay. You can just do that. There is not much insight by multiplying the terms together. You can multiply it if you want, but there is no need to do that. In this particular case, there are some terms you can cancel out, right? You could have 2x. You could have 6x cubed minus 2x cubed, so that's 4x cubed. But beyond that, there's not much you can do. So we just leave it like that. And this is an example where the slope is more complicated than the original function. That could happen. Finally, the last rule we're going to talk about today, the chain rule. The chain rule deals with what happens when you have one function within another. So let's say the definition is a bit complicated, so let's see what it means. So if g is differentiable at x and f is differentiable at gx, why would we have something like that? Because you see, what we're interested in is f of g of x. So the value, g is taking on at the moment is gx. So that's why it has to be differentiable at x. Then f is taking on a value gx. So that's why f has to be differentiable at gx. When that's true, then the derivative of f of g of x equals to f prime gx times g prime x. Okay, so let's first see an example, because first seeing an example is probably going to make it easier to understand. How do you take the derivative of square root of x to the power 5 minus 2x plus 4? How do you find the derivative of something like that? Well, here's where chain rule would be helpful. You can think about it as this way. F of x is root x. Gx is x to the power 5 minus 2x plus 4. So what you have here is actually ddx f dx. According to the chain rule, this equals to ddx. It's probably better. Well, okay. According to the chain rule, it equals to f prime x, f prime gx multiplied by g prime x. What does that mean? F prime x, that is the derivative of root x. The derivative of root x is root x is x to the power 0.5. The derivative is 0.5. Whatever is inside x. And then 0.5 minus 1. This is the fx part. So maybe I use different colors to indicate it. 0.5, 0.5 minus 1. So this is from fx. And I'm going to use red to represent gx. Okay. Gx's. According to chain rule, you have to copy whatever does gx inside. And then you have to take the derivative of gx and multiply it at the back. So what would be the derivative of gx? That's derivative of 5x, which is 5x to the power 4. Then minus the derivative of 2x, that's minus 2. Then plus the derivative of 4, which is 0. So this is what the slope of this function is, according to chain rule. And once again, in this particular case, all you need to do is, well, you can put it in half if you want, but it's not necessary. X to the power 5 minus 2x plus 4. And this one you probably want to say is, once again, it's up to you whether you want to put it in a fraction or you just want to leave as negative 0.5. That's okay. And then 5x to the power 4 minus 2. Okay. If you want, you could also put it like this. That's identical. It's up to you. Why is it called a chain? What is it called chain rule? Why is it called chain rule? It's called chain rule because you could apply this process infinitely many times as you need if you have many compound functions. The derivative of f of g of hx, you could do that. You have three functions nest together. The chain rule says this equals to f prime g of hx. Now beware of the number of brackets you have, 1, 2, 3, yeah, that's correct. Multiplied by g prime hx multiplied by h prime x. So it's called chain rule because the more functions you have inside, the more terms you have to chain at the very back. You have f, g, h. Three functions nest together, you have to have three parts. So there is not, do you need to consciously think about when to use chain rule? You don't really need to. Well, because once you see that when you have a function where there's no rule directly for that function, then you have to use the chain rule, right? There is no rule for root x cubed minus 2x plus 4. There is a rule for root x, the power rule. So that you need to use the chain rule. First, figure out what the derivative of root x is. Then instead of x, you put in whatever is inside the root here. Then you have to remember that you have to take the derivative of whatever is inside at the back. If whatever is inside is still too complicated, like if it's another square or like a cube or something, right? Or in the future, next week, we'll be learning when you have log, exponential functions. You have these kind of things inside. So then you use the chain rule again, like in this case, right? So you'll see more examples of that in the tutorial. Remember, we have 2 tutorials starting from last week. So we have one today and one tomorrow. They will be identical, so you can choose which one to go. Okay. So that's all for today.